It is an honor to share with you the presentation of the book Seismic Isolation for Architects for the Turkish Association for Seismic Isolation and for the Anti-Seismic International Society, ASISI, here in Istanbul. I want to thank you to Dr. Bahadir Sadan, who planned this seminar, to Dr. Ian Aiken, to MEF University, to FADA, Faculty of Arts, Design and Architecture, and the generous and unconditional support. Unconditional support of Rodrigo Retamales Saavedra, advisor of my PhD thesis in architecture about earthquake architecture. This conference is based on our book and updated with my current research. Here, I come from the province of Mendoza, Argentina. Mendoza, Argentina. And Andrew comes from the other side of the Circum-Pacific belt, from New Zealand. And we have different areas, different belts here in Istanbul from the Eurasian belts. We are from different belts, but we have the same problems, a very serious problem. Architectural design conditions the behavior of the structure. In the following photographs, we observe a very common characteristic of architectural designs, which is that the free floors on the lower levels, the phenomenon of a weak floor or flexible floor. The need for large spaces requires that the structure be mainly made of porches, and the functions of housing, offices, and other mainly require walls. The change in rigidity is very important, concentrated in these levels where the efforts are very great. The result is failure at the bottom, with extensive damages until it collapses. How many lessons do we still? Sorry. How many lessons do we still need? Lessons from 1995 in Chile, in Palu, in Huaylén County, here, and Huaylén. This year, the same problems, architectural problems. Designers, architects, and engineers must achieve resilience in their projects. This book introduces a relatively new game-changing technology to a wider audience. Many books and articles on the seismic isolation of buildings have been written for structural engineers. However, these publications was highly technical in nature and therefore are unsuitable for the vast majority. To others who designed, construct, own, insure, and inhabited buildings in seismically active regions. The purpose of the book, then, is to introduce a relatively new game-changing technology, as we said. The objective of seismic isolation is preventing the seismic energy entering to the structure, separating from the building from the ground using devices located between the foundations and the building. In this way, they filter the vibrations produced by the earthquake drastically, reducing the probability of damage. They can be placed between the building itself and its foundation, creating a layer between the building and the ground. I'm sorry. I need to point. Sorry.
I think this one. No?
Okay.
Yeah.
Thank you. Here you can see the deformation in the conventional buildings, the important damages, loss of lives, and economics, unsuitable designs in conventional buildings, no guarantee in the intended purposes, no limit damages of or the operation of the strategic and essential functions. It is not resilient. In base isolated buildings, the deformation are very little without the importance of the damages, no loss of lives, and the minimal economical losses. The design is sustainable. It guarantees the need purposes, drastically limits the damages, and does not interrupt the operation of strategic and essential functions, and it is resilient. This is how it works.
Press enter. Again.
I'm sorry.
Here, no problem.
I'm sorry.
I need to return back. Okay, like this.
Thank you.
Then you will need to again press here.
Yes.
Okay?
Yes. You can see here the conventional buildings, deformations, damages, and here the building remains quiet and soft. And this is isolator. It's magical for architectures. The most used seismic isolation are lead rubber bearings and curved slider pendulum. Elastomeric isolators consist of a series of sheets of natural rubber and steel braced alternatively and bonding together to form a device that supports the lid of the column or plate. They have similar mechanisms. Leather rubber bearings diameter are typical from 60 to 115 centimeters, and the slider bearing diameters from 15 to 20 centimeters. The difference is in the height of the device. LRB are typical to 30-40 centimeters tall, while VPS are 15 to 20 centimeters tall. This is the way of an elastomeric lead rubber bearings works. This would be the upper plan would be the building, and this would be the ground with an earthquake. And the curved double pendulum bearings works like this. They work by separating the movement of the structure from the movement of the ground, preventing earthquake energy from entering to the structure. In the case of lead rubber, the energy dissipation is through horizontal at yielding the lead core. In the case of double pendulum sliders is through the friction that occurs during the horizontal displacement. The double friction pendulum seismic isolator works under pendulum principle. This device allows horizontal displacement of the structure, providing the necessary change in its natural period when activated due to an earthquake. The important thing about the frictional pendulum, unlike the elastomeric one, is that it allows light structures to be seismically isolated. The earthquake-resistant architectural goals are improve people's comfort, protect investments, protect contents, continue business operations, reduce damage repair costs, the response to the emergency, protect architects' work, occupant safety, peace of mind, and of course, resilience. We encounter seismically isolated hospital and emergency responses centers and buildings housing, manufacturing, or other functions for whom downtime following an earthquake would be disastrous. The contents for some buildings are more valuable than the buildings themselves. Frequently, owners desire to minimize damages to repair costs. Perhaps their investments in seismic isolation is an alternative to paying earthquake insurance premiums and allowing early, if not immediately, reoccupancy for a building following an earthquake. There are also many buildings of historical significance that have been seismically isolated. The architectural benefits of seismic isolation. Pre-earthquake benefits. The benefits are realized before the occurrence of a damaging earthquake as well as during and after such an event. Many benefits, including insurances, premium savings, can be realized even before an earthquake strikes. Others occur during the design phase of a building when they can lead to improved architectural features. During the event, protection of life, contents and buildings, and after, while the pre-earthquake benefits isolation are tangible. How much more so are those incurred during and after a large earthquake? Did reduce distress, reduce injuries to buildings, occupants and passers-by, nor or minimal structural damage, nor or minimal damage to architectural, non-structural elements, and nor minimal disruption to building occupancy and function. The effects of such considerable reduction in drift and acceleration mean no structural damage in minimal damage to architectural elements and building contents. Now we see some buildings designed with seismic isolation from the conception of the project idea. The use of seismic isolation has expanded to different applications, including hospital, airports, condominiums, data centers, commercial buildings, industrial facilities, educational, museums, and more. Inagi Hospital. This is one of the first Japanese public hospitals projected with base isolation from the beginning of the project. It achieved morphological improvements which were considered dangerous. The building shape derives from the need to concentrate vertical circulation in the center, a complex morphology which is not advisable for a seismic area. This allowed the improvement of its architectural operation since it was necessary to place the infirmary in the center to have a lower traffic of the personnel. The use of the internal space was optimized of the different needs. Admission beds were increased by 30%. Patients enjoy more privacy and comfort with natural lighting and ventilation. Thanks to this system, the building could achieve this configuration. This building is supported 168 isolators after several significant earthquakes, it continued operating, achieving durability and continuity of architecture over time. The necessary beauty, which makes the city more attractive and beautiful, was finally obtained. The Hospital Militar of La Reina in Santiago, Chile, thanks to the use of base isolation, a huge interior space with triple height was obtained to have light and ventilation in all the rooms, outpatients, surgeries, and offices. It is supported by 160 elastomeric isolators. The building dimensions are 126 meters by 116 meters with no structural joints. It has 4 levels and 1 level underground. The isolated system was installed on the top of the underground level used for parking purposes. In this way, the construction of an additional slab was avoided. The use of base isolation in this building reduces 3 times the stress and deformation in the superstructure. This building had an excellent performance during the last earthquake in 2010. It worked almost immediately and did not show any damage at all. The adjacent building, conventional, shown in the top right photo, this building, this building is not isolated and exhibited severe non-structural damages. Thus, besides being functional, the building enriches its environment with a contemporary image that shows resistance and solidity in case of earthquakes. You have the largest base isolated building in the world here in Turkey. Covering more than 1 million square meters with more than 2,068 triple friction pendulum isolators. A huge platform over the isolators are located in the parking floor. Bahadir could talk about this building later if you want. It's marvelous, this building, this hospital. This terminal is located in a seismically active region with 2 branches of the North Anatolian Fault in close proximity here. Maybe we can feel some earthquake to feel a better seminar. Preparation for earthquakes was a vital part of the building design, include domestic and international terminal building, parking structure, hotel, and new VIP terminal. The isolator at Sabiha Gökçen Airport are pendulum bearings. The area if 200 meters square, and the passenger capacity are 22 millions. The terminal comprises 4 stories above the basement floor, below the isolation plane. It has steel structure with plan dimensions of 160 per 272 meters without floor joints, and a total building height of approximately 32 meters. The whole terminal building sits on a platform that is to a high degree isolated from the ground below. This enabled a team to design the terminal almost as thought it were situated in a non-seismical zone. It's marvelous. This system is amazing. Here you can see this fantastic interior space, and thanks for the use of base isolation, a monumental huge interior space was obtained. Tots Omotesando in Tokyo by Toyo Ito, architect, a creative language of great plastic expressiveness is achieved, using environmental elements as inspiration. The tree. It is an L-shaped architectural design without structural joints. There is a protection of patrimony, beauty, significance, communication, and culture. After a major earthquake, activities continue normally. Prada Boutique Aoyama Building, architectural design of innovative formal expression were achieved. Sculpture formed with respect to immediate urban context. Base isolation system is under the basement. Therefore, a perimeter space was necessary for the free movement of the building. The horizontal loads were reduced in the structure, allowing thus the use of rhomboidal grid made up with big glass sheets. Architects must know that we need free space separating the fixed and the isolated part. It's essential. Templo Bahá'í in Santiago de Chile, its creators define it as an undulated mantle. They are structures composed of 3 layers, the internal one of alabaster, the external one of molten glass, and the intermediate one of the stainless steel, which contains the previous one. Freedom of architectural design with the minimum security achieved by the current state of the art. You can see the undulated mantle. Innovative design that could not be built in a highly seismic area like Chile freedom in architectural design, both spatial, functional, and plastic. Freedom of the use of materials. It has unconventional construction materials, such as alabaster and a bath of liquid glass on the outside. The design includes 10 isolated devices, allowing a reduction in the cost of the superstructure. The structure is designed to remain for 300 years. A large, innovative, dynamic, volumetrical space was designed with a great plastic expressiveness not previously achieved in seismic zones. Thanks to the use of base isolation, each petal of the structure is composed of a stone skin as a cover, which will allow it to be a pole of light at night. This small chapel couldn't be in seismic place like Japan. The freedom in architectural design was possible thanks to base isolation system. This contemporary cathedral was designed with medieval criteria, that is, highly strong elements when expressing durability through times. It should last 500 years. The complex geometry of the construction was possible because of the use of base isolation. Huge volumes in the interior space were obtained, and outstanding images of resistance against earthquake is shown. The building has not been damaged with the frequent tremors. The isolator's location is hidden. You don't know if this big cathedral is isolated or no. In this example, the designer wished to show the system in a plastical language of architecture. The location of the 8 isolator is part of the architectural design. Here you have the 8 isolators, and they have a protection. I cannot see. A total of 145 and also 4 sliders located at the underground level at strategical points according to calculation in this university. Base isolation reduced seismic acceleration, thus allowing for the structure irregularities and discontinuities inherent to the project. The architecture has a morphology that expands boundaries of design comfort, and safety in seismic zones. Due to the use of seismic isolation, this building has complex and atypical geometry and characteristics for seismic zone, an irregular structure in plan and height. Plans have large openings in the diaphragms. All levels are different. Cantilevers more than 6 meters in length. Greater spatial wealth, comfort, sustainability. All levels are different. The transmission of loads is not direct. The seismic isolation system is not visible. It does not interfere with the plastic of the architecture. The use of seismic isolation makes it possible to make a highly transparent corporate building viable in an area of high seismicity. Seismic isolation is located on 2 levels, under the ground level in the perimeter columns and under the elevator shaft in the central wall area. Isolation for data centers is essential for operational continuity. This small mobile center is a container mounted on low mass isolation system isolators. We can isolate everything. This data center was designed to protect the continuity of operation, exhibiting annual downtimes less than 8 minutes to achieve Tier 4 objectives according to Tier standard. The IMT Shinoshaka building is a company-owned dormitory. It utilizes high damping rubber bearings. This structure was designed to be a highly earthquake-resistant building for Shimizu engineers, managers, and researchers to use as a location from which to respond to the future Kansai area earthquake. Seismic isolation devices on columns heads on specific floor, such the first floor, compared to installing seismic isolation devices on foundations. A construction with seismic isolation was being carried out effectively and at a lower cost. Here you can see this atypical capital of columns. This is a low-cost housing. It has 2 isolators. The isolators are responsible for making the house return to its original position after the earthquake. The other device is this column that has spherical form. So this can move in this way, and then the 2 isolators return to the primary position. Let's see two retrofitted buildings. China Basin Building in San Francisco, California, has an old building existing in the port and it has to be restored. And two more levels aimed at offices were added. A contemporary architectural language is achieved, revitalizing the environment and using a space not available before for a new construction. It was built in a place where there was not place at all. The base isolation interface is at the top of the building, and the new construction does not transfer major horizontal loads. The work cost has reduced in the short and long term. In this example, the base isolation system is hidden. In this way, the heritage wasn't altered with any exterior structure. This building is from Le Corbusier. This building. This is a joke. We not have a break, so we will continue. Oh. And we will talk about confidence. Sorry. Thank you, Bahadir. Thank you. Confidence in base isolation system. Only 6 isolators were used in a building like a bridge. And this is the behavior in an earthquake, in a real earthquake. You can see the movement of this column, and the camera is on the floor up. You can see the movement here, and the building stands and doesn't move. Really, the system is magical for architects. And it is a successful behavior of Malatya Hospital here in Turkey last year. The earth moves and the building is not moving. You can see the behavior here, and these kind of details that architect must know to solve. Here. remember that only the Earth is moving, building, no. Amazing. There are 5 requirements for seismic isolation. Architects need to be aware that while the capacity for horizontal movement is the first requirement for an isolated structure, there are 4 other requirements as well: vertical support, recentering, restriction, and damaging. This works very fast. Movement capability is provided by elastomeric bearings from natural rubber or sliding surfaces and silent steel, and otherwise complete separation of the structure from the ground. A recentering or restoring force keeps bringing the superstructure back to its original position while preventing motion during wind gusts. Damping lessens the relative horizontal movement between the superstructure and foundation, reducing the cost of bearings and other details. It is important the width of the gaps that accommodate the movement. Architectural benefits of base isolation: reduce interstory drift and possible lower levels of strength and ductility can be exploited in more elegant detailing and more slender and less regular structure. Numerous case studies illustrate how architects are taking advantage of seismic isolation to reinforce and achieve a wide range of architectural objectives. Charleson points that the case studies are grounded in 4 categories of architectural concepts and qualities that encapsulate prevalent architectural concepts and qualities in contemporary architecture. The categories most relevant to seismic isolation architecture are grounded and floating. The structural configuration unthinkable in conventional buildings can be considered in isolation buildings. More slender columns and structural walls are also feasible, as well as simpler and thinner separation gaps. These potential benefits can improve architectural aesthetics. Tots homotezando, at the base of the building, the structure is dense, but higher up it becomes more delicate. Here. Tama Art University Library in Tokyo, part of the 2 main facade columns touch the floor very lightly. Heavy and lightweight. In Aji Hospital, Tokyo, a complex butterfly shape plan. Prada Boutique Aoyama, front entrance, Japan, from Gerson and de Meuron. It's an example of structural lightness. Stability and instability. In auditorium in L'Aquila and the River Chapel in Japan. The other quality, the building can be simple or complex. This building, the simple one, is in Mendoza. Well, we just talk about this. I put it here to convince architects to think about base isolated systems. Of course, the system have some limitation. The effectiveness and application of seismic isolation can be limited by adjacent buildings. It makes light dense to isolate a building that is adjacent to one that is more vulnerable. A seismically isolated building should not be built adjacent to a more vulnerable building. All buildings must be set back on their sides to avoid pounded neighboring buildings. For seismic isolated building, almost all horizontal movements occurred at the plane of isolation. The cost of implementing seismic isolation technology in South America. This information is from Rodrigo Retamales. $20 per square meters for civil works, beam above and below isolators, additional excavation, expansion joints, cover, etc. $20 per meter square for seismic isolation system, including prototype and 100% production testing, transportation, insurance, and transportation to site. Above values valid for built areas greater than 10,000 square meters. For built areas larger than 100 and 1,000 square meters, the costs are reduced by a factor between 2 and 3. For built areas smaller than 10,000 meters square, the costs are increased by a factor between 2 and 3. The other requirements for seismic isolation is the need a technical level for inspection and devices and replacement them is if necessary. You can take advantage of this space by using it for parking like in other examples. another requirement: design details. The successful introduction of any new technology into a design and construction project necessitates additional communication and a higher level of collaboration between members of the design teams. Once a decision to seismically isolate is made, the intensity of collaboration increases. Architects are responsible for the design of the moat and the cover inspection joints. Cover plates are available in many different forms, ranging from simple, high visible surfaces mounted plates to those that are concealed, and they may incorporate additional complexity to provide fire resistance and rainwater collection across the gap. Maybe here you cannot see the gap. It is here between the stairs and the building, and this small platform is the cover plate of the gap. As well as moat covers and other flooring movement joints, capacity for seismic movement is also required when an isolated building connects to another building, be it isolated or not, at the roof, up walls, and along and across ceilings. Look at this movement. The cover of the gap. The center part is a fixed building, and the others act as base isolators. This man is not, he don't feel the movement. Say again, architects are responsible for the design. They are not complicated, but we must know that we have to take into account the design with the connection from the movement of of the ground and the base isolated building. In this case is this platform, and here is the free space of the gap. An external secondary stair, the landing cantilevers from the isolated building to a right and slides on the supporting pier. The handrails are separated to allow movement. A precast moat cover where movement parallel to the entrance is accommodated by the nearly angle sliding joint. Movement at right angles occur when the precast slabs slide along the steel support rails that are attached to the isolated structure. This is in Tokyo. Here you can see the fixed part and the isolated part. And this cover can move, leaving the future. This is a relative new building. It is very innovative form that it couldn't be possible in seismic areas. This is an example of part of the edification, and you can plan the render and you will have almost the same in the real life. And this building rotates 90 degrees. We are living the future. All these advances are expected to result in safer buildings and communities as more building owners, architects and engineers request or recommend the application of seismic isolation in their buildings. Seismic isolation has a very promising future for innovative and safe architectural design. Thank you very much for your attention.
Thank you very much. Thank you very much, Adriana. Do we have any questions from the audience? You can ask in Turkish also. Türkçe'de sorabilirsiniz. Soru falan varsa. Tamam. Bir ikinci mikrofonu da ayarlayın bir saniye. Ses. Adriana, let me give you this.
Hi.
Hello.
My name is Onur, and I wanted to ask you something. As you know, the earthquakes concern, Istanbul is located in a risky zone, and a serious earthquake is expected in a few decades, maybe. And about the seismic isolators, I wanted to ask if there's a limit for them to operate after the earthquake. I mean, about the magnitude. Is it relevant for the seismic isolator to keep operating after the earthquake or not?
You mean the magnitude of earthquake?
Yeah. Does the magnitude of the earthquake matter for the seismic isolator to still operate after the earthquake?
The design of the building is for the maximum earthquake, yes, possible earthquake in the zone.
So it should be decided exclusive, special for the design itself. So
It is considered in design.
yeah,
The building is designed for maximum credible earthquake, so mostly the earthquake that will happen should be less than the designed.
yeah.
Level.
So is there difference between the types of isolators that you've shown previously? You have shown few types of isolators, but
Yes, the way that they work, it's very similar. But one is from lead rubber and the other is by Teflon and
Stainless steel.
stainless steel. Yes.
thank you so much.
Thank you.
Questions?
We have seen gaps like between the fix and the
Mm-hmm.
like the
Isolated.
isolated area. All the fix can like move, right? Because as far as I see, like some of them seem like it's like fixed, like between the like that's areas.
I
Like all the gaps are like the platforms we put between the gaps. All of them can move, right?
Sure.
Because
all the buildings must move. So you can put the platforms, yes, from the isolated building to pass and move in the
The ground.
in the ground. So the cover will do this.
In all directions.
Mhm.
Any other questions? Türkçe de sorabilirsiniz. Ozan Bey. Evet.
Thank you for joining us and explaining your knowledge and different examples from the world. Just, it's not a question directly, but I want to remind and add something to your very good submission. First of all, it's very good to hear these kind of discussions or these kind of techniques from the architecture side, because until now it was the in the leadership or in the responsibility of the structural engineers. So everybody maybe in this area learn the subject from other men, like civil engineers. So we civil engineers try to have more experience than the architects and the different discipline owners or responsible. The idea is it's something out of the disciplines. It's not only architectural,
Yes.
it's not only structural. Maybe in the new era, a new kind of engineering or architectural and engineering will occur. And with our knowledge combined together, we need to think about, as you say, I can say there are 7 different principles of a seismic isolated building, including the non-structural elements, the sliding floors, and the electrical and mechanical connections, the elevators design, or even the rain pipes shall be designed in different ideas.
Mm-hmm.
So it's not only the seismic isolation, but also all these
Yes.
items will help the building to stay safe in and after the earthquake. So what we have to focus is, number one, is to describe what is seismic isolation, because audience do not still know. Second, in our region especially, the architectural companies care about the square meter, because as you know, our columns are a bit more square shaped in these isolated buildings. But they prefer not to see any columns. They need to hide it into, I mean, they or you, the architects.
Yes.
So still, let's say in the morning I spoke to personal, special architecture company, they are still saying, no, we cannot make square corners. So this is number two. People have to understand that design or safety, which is the priority. And last, we can discuss the multidiscipline solutions. But I think we have a couple of 10 years more to accomplish this all together. Thank you very much for attending. Thank you very much for coming to Turkey and share your knowledge with us.
Thank you very much.
Thank you very much.
Thank you very much for the comment. Any other comments or questions? From one architect to another.
Yes.
Ah.
This is Adriana Guisasola. I am an architect for about 30 years. Adriana, you are from Argentina. We discussed this situation in Turkey that the weakest partner chain of the organization responsible for thematics is the architect in our country. I realized this about 10 years ago because we are still learning from engineers as per owners' requirements.
Mm-hmm.
The weak part is architect in Turkey, as I mentioned, because I am curious about your country. What is the situation in your country?
Right.
Because the electrical engineers, mechanical engineers are dealing with the details, they are aware of the details as for the building design, whatever. But the engineers, civil engineers are very much experienced in our country. They are experts here.
Mm-hmm.
Owners, before the Kahramanmaraş earthquake, we had two big owners, in fact, investors as public, from the public side, Ministry of Health and the Ministry of Transportation, and after this big disaster, now the owners are changed, the private owners are added also. They mostly know what they want. The civil engineers know how to solve the problems. The electrical engineers, mechanical engineers are okay. They are above the average, but the missing part is the architect in our country. So, you should kindly explain what is your situation in your country.
In my country, there are no several base isolated buildings. It's a new way of thinking about. But architects don't like that part of the building. So they say that the responsibility is for the engineer. And it is so sad and so dangerous. But I think we are growing and we are living in the future, I think. Is that the reason that I came in my vacations to share with you some of my knowledge?
Thank you.
Thank you.
Next time maybe we have to come to your country and share our knowledge and
Oh, I will wait in you.
near future.
Any other questions, comments, English or Turkish? Sanırım başka soru yok diye düşünüyorum. I think the questions are over.
Okay.
And it was a lovely presentation. Thank you very much. I mean, we are always showing some isolated buildings in Turkey, in the world, but those buildings that you showed really reflects the superiority of building design using seismic isolators.
Yes.
So it was very important.
Yes.
Thank you very much for sharing this.
A
And
pleasure.
probably the people will ask if they could have your presentation. Nobody asked, but I'm sure you will be asking. If it is possible,
Yes,
yeah,
of course.
okay, we would like to share it with the audience. Once again, thank you very much.
Thank you.
We have a
Bahadi.
small gift for you. We will give it the chair of Civil Engineering Department, Gökçe Hocam.
Oh, thank
Let's
you.
do it together.
Thank you very much for your presentation and sharing your ideas with us.
Thank you.
As engineers, we really like to cooperate with architects, especially for a safer future
Yes.
for all of us. That was really very nice to hear your ideas. Thank you very much.
Thank you.